I wanted to say just a few words on behalf of all the organizers to introduce this special session. So as you might have noticed, the talks of the previous days focused on systems with quench disorder, such as spin glasses, optimization problems, inference problems. So these are the systems for which the replica method was originally designed and for which replica symmetry breaking was discovered 40 years ago. But soon afterwards, it was recognized by Kirkpatrick, Tirumalai, and Volines that particle glasses that have no quench disorder could also be described using similar ideas and tools. And so we believe that this was a major intellectual breakthrough. And one of their most influential papers, which is this one, was published exactly 30 years ago. So, and these ideas have been inspiring for the whole glass community over the last 30 years. So this is why we decided to have a special session to celebrate the 30th anniversary of the formulation of the random first order transition theory. And we are very honored that Professors Kirkpatrick, Tirumalai, and Volines accepted our invitation to join us and participate to this session. So we asked Jean-Philippe Bouchot to begin the session by some historical review of these developments. And so, okay, we hope you will enjoy this session. And with this, I pass the microphone to the chairman, Mike Moore.
Thank you very much. Well, you may have noticed already that your chairman belonged to the distant history of spin glasses, and I'm one of these, but I belong to the dark ages of spin glass work before Giorgio came along with his actual hierarchical replica symmetry breaking scheme. In 1978, David Thouless, in his paper with Almeida, had already suggested that the way out of this negative entropy in the SK model was to break replica symmetry. And I remember meeting him, and he said, well, I suggested it, but I don't want to do it because there's an infinite number of ways of breaking the replica symmetry. But Alan Bray and I, we just went ahead and divided the replicas into two groups, M in one group, N minus M in the other, and calculated. And by taking M off to infinity, we got a solution which had no negative eigenvalues in the Hessian, which David felt was a bad idea. But unfortunately, there was a little technical problem. The value of Z to the N, as N goes to 0, should equal 1. But in fact, it wasn't 1. It was an exponentially large number, which just happened to equal the number of solutions to the TAP equations. And this is clearly not a good thing to have for the limit of n going to 0. But this work led to applications which were useful in instantons, in analyzing the systems which are marginally stable. But after that paper I received Giorgio's papers to referee. And I was one of the people who may have been mentioned already. And I remember because of the scatter amongst different journals, I was getting them all at the same time. And so I got the early papers where there was just one-step replica symmetry breaking to go to the later ones. And I was tempted as a referee to say, well, the earlier ones, the one with one-step replica symmetry breaking, should perhaps be just dropped in favor of the later ones. But if that had happened, perhaps we wouldn't have been having this session this morning. So let me hand it over to you.
I think I have a microphone. Okay, good morning. So I'm really happy to be in Rome as usual. I think it's my 50th anniversary of coming to Rome for the first time, just for the fun of adding anniversaries. But I don't know if I want to thank the organizers because they gave me this treacherous and daunting task to review RFOT for you. So it's going to be a short review, partial review, probably subjective review, and it's going to be influenced by many work that I did with many people, particularly Giulio Biroli, and conversations I had with many other people over the years. It's also the opportunity to say all my admiration to Kirkpatrick, Tirumala, and Walliness are heroes of the day. So this is without flattery. It's really, I think, one of the, as Francesco said, one of the major breakthrough and intellectual advances that were made possible, after all, by Giorgio's RSB, who afforded us with a method that's probably as useful as Fourier transforms for disordered systems. So what was known pre-80 about glasses? So I'm going to show curves that are so well known that they become corny now, but I just want to remind you, the basic phenomenology of glasses. So actually there are different glass transitions already at the time, temperatures, 3 at least. So the traditional glass transition temperature, where the relaxation time reaches an arbitrary number, 1,000 seconds. And what was known is that the relaxation time increases extremely fast, close to Tg, actually super Arrhenius. And that's the famous plot where this log of relaxation time is plotted as 1/T. And you have to remember that for fragile liquids, it's really a very impressive increase that you see. The relaxation time increases by 10 orders of magnitude when the temperature decreases by only 10%. There's, around this glass transition, or effective glass transition, there's no latent heat, but a jump in specific heat. And as the glass appears, as it becomes rigid, which is its most important physical property, it does so in a discontinuous way. The high-frequency shear modulus that becomes lower and lower frequency jumps from essentially 0 to a non-zero value as Tg is crossed. The excess entropy of the glass as compared to the solid is large. It's several kBs per molecule. This has been emphasized by Peter, actually. And this entropy appears to vanish at a different temperature below Tg, below the glass temperature, which is called the Kautzmann temperature. And so here you see graphs of these entropy extrapolating to 0 below the glass temperature. The dynamics seems to cross over from an essentially unencumbered flow at high temperature to something that becomes activated, or as Goldstein called it, landscape dominated. And this appears at another temperature, T star, above Tg. And the last thing that I think caught the interest of many of us is that this dynamic slowdown of glasses seem to have a thermodynamic origin, in the sense that there seems to be a correlation between, for example, the entropy and the log of the relaxation time. So the Adam-Gibbs relation is that the log of the relaxation time is just the inverse of this excess entropy that seems to extrapolate to 0 at Tk. This is quite a good empirical correlation, both in temperature and also cross-sectional across different liquids. And finally, something that's not really experimental, but there was this suggestive idea of Adam-Gibbs that there must be a cooperative length scale accompanying this slowdown. And I always found the argument pretty woolly, but essentially it says that this cooperative length scale must be such that there's at least one state to relax to on that scale. So the excess entropy times the cube of this length has to be something that's over the 1. Okay, so that's essentially the challenge that was to be explained back then. And as I said, the most important thing about glasses is that they're not flowing, they're rigid. And Phil Anderson said, well, some but not all transitions to rigid glass-like states may entail a hidden microscopic order parameter, which is not a microscopic variable in any usual sense, and describes the rigidity of the system. So Anderson thought that spin glasses would be a kind of appetizer, a walk in the park, before addressing a more complicated problem of glasses. And indeed, as we know now, spin glasses have a transition to something that's weird. It has a transition towards something that's frozen but amorphous, so a kind of amorphous long-range order. But compared to glasses, it doesn't have the right phenomenology. It's a second-order phase transition. And in particular, what's, I think, again, remarkable when you think about it from a naive point of view, is that this transition to an amorphous order is accompanied by a divergence, and the divergence is the divergence of the nonlinear susceptibility. So these are experimental data by Laurent Lévy, I think, where you see that as you reach TK, this third order susceptibility actually diverges. So in order to understand spin glasses, we've heard about the SK, which is already a toy model of spin glasses. And then we heard about the REM by Bernard yesterday, which is a toy model of the toy model. And he explained all this yesterday. And it's an amazingly simple, but an amazingly rich model, because it's a generic model for this mixed type freezing transition into something random at low temperature. Because by definition, the random energy model has no structure. You freeze into something that's random by construction. The entropy goes to 0 linearly as the temperature goes to Tk, to this Kautzmann temperature, with a jump of specific heat and a jump in the Edwards-Anderson parameter that is the degree of freezing, if you want. And of course, in the paper by Bernard, there's also this amazing invention of a new family of models. He explained yesterday, the p-spin models, which I think open the path to many, many things that we are all doing now. The REM is just the limit when p goes to infinity of that. So this is the graph of the log of the number of states in the random energy model, and that you see that it goes to 0 linearly close to the ground state. And actually, that's not so trivial. If you throw at random two-level systems, then you won't get this linear vanishing. Actually, you'll get square root behavior. So it seems that this thing requires some kind of strong interaction between individual elements. Okay, so now we're going into what I call the roaring 80s, where everything happened. And what's interesting is that it happened from many directions at the same time. So the p-spin were studied as spin glass models, and the phenomenology of the random energy model seemed to exist for all p larger than 2. Simultaneously, Peter and others found that density functional Hamiltonians for liquids seem to possess many amorphous minima at below some temperature or above some density. And simultaneously, again, from a completely different community, mode coupling theory was developed as a closure scheme of dynamical liquid theory by Goetze and collaborators. And this mode coupling theory predicted a discontinuous dynamical transition at some temperature Td, and was shown also to be able to reproduce many interesting facts that people were seeing in neutron scattering experiments or other type of experiments. So a lot of the phenomenology of MCT was used to fit experiments, if you want. And then I think the breakthrough came that these mean field p-spin models have a dynamics that is formally equivalent to MCT with a purely dynamical freezing transition at a temperature Td greater than Tk, the thermodynamic transition of Derrida, if you want, or of Kautzmann. And furthermore, that from a thermodynamical point of view, nothing happens at Td. It's a strange transition, a kind of fragmentation transition in phase space that I'll illustrate in a second, where the liquid state, which is kind of one and unique at high temperature, becomes the superposition of an exponential number of dynamically disconnected pieces. And all these pieces are actually amorphous minima, all of them having a free energy that's larger than that of the liquid. So this is all in these papers. Yes, I've used this kind of side note way to give references, and of course there's a lot missing, but I've selected a few that I find relevant. So this suggests, compared to the phenomenology of glasses that I reminded you before, a tantalizing scenario that above Td, all relevant thermodynamical configurations are unstable. Locally, the Hessian has unstable directions, so it's a free flow, unencumbered dynamics. But below Td, at least in mean field, all the relevant configurations are local minima from which you can't escape because barriers are infinite. But if these barriers could be crossed, then one would recover exactly the free energy of the liquid. That is, the energy of the liquid turns out to be exactly the free energy of these dominant states at a given temperature minus T times the log of their number. So it's really a precise incarnation of this Goldstein MCT scenario with a temperature T star equal to this dynamical transition, and also a precise analytical theory for glasses as just a frozen in liquid in a very precise sense. And so this is the phase diagram that is traditional now, where above TD the liquid state is unique, and below TD it becomes fragmented in many little pockets. And of course this phase diagram is now universal and seen in many different optimization problems. So this is the free energy of the liquid. And then at TD, nothing happens. The free energy of the liquid just continues with no singularity. But actually, microscopically, if the dynamics doesn't allow any crossing of the barriers, then you're stuck in one of these bubbles, and you have a free energy that's above. It's only by subtracting the configurational entropy, i.e., allowing the system to visit all of them, then you're able to recover the liquid. So I think it's something very beautiful and very surprising in the way Rudolf Piles would speak about surprises in theoretical physics, is something that was hard to anticipate without an analytical theory. You could argue that maybe something happens like this, but to get such a precise incarnation of vague ideas is, I guess, very remarkable. Okay, but so in finite dimension, one expects these barriers to be crossed, and then comes this paper that Francesco told you about already, which is probably at that moment that myself I got aware of all this. And what is argued in that paper is that ergodicity restoration, the crossing of the barrier, arises from a kind of nucleation argument, like transitions that exist in mean field that are destroyed by nucleation in finite dimension. And so the argument of this paper is to say that there's an entropic driving force coming from this configurational entropy that is somehow counterbalanced by a surface energy between different states that scales with the size of the bubbles to some exponent theta, and y or epsilon here is some kind of surface tension. And if you assume that something like this is the case, then what's interesting from a phenomenological point of view is that you can derive immediately a length scale that is inversely proportional to the configurational entropy to some power. And you remember that this configurational entropy actually goes to 0 at Tk, like in the REM. And so there's indeed a kind of Adam-Gibbs cooperative length that diverges as T goes to Tk. If you assume that barriers scale like either of these terms, which are actually the same, then T log tau is going to grow like this. And this gives back a super Arrhenius Vogel-Fulcher type of law, and these Adam-Gibbs correlations between thermodynamics and dynamics that I talked about. And in this paper, KTW argue that theta should be d/2 and that epsilon should be proportional to temperature. And in this case, actually, you get not only Adam-Gibbs phenomenology, but you get actually exact Adam-Gibbs, an exact Adam-Gibbs relation between log tau and 1/s. But then, as I said, I read this paper maybe in 90. It was close to the time you visited École Normale, so I can't remember exactly when that was. But and I was completely puzzled by your paper. Okay, so I was rambling about what you had done maybe for 2 or 3 years, and I couldn't really make sense of your nucleation argument that somehow gets interrupted at this scale psi, and leads to what you call the mosaic state. But at this point, I think that something that was somehow missing in the picture. Okay, so now I'm going to go to the 90s and the noughties, where discoveries and reformulations took place. So as far as I remember, it's only around 93, 94 that the P-spin MCT connection sunk in on this side of the Atlantic. I think we kind of rediscovered some of the things that, of course, you had done. And it took us some time to realize that there was this deep connection. We also became excited in this idea of self-induced disorder and replicas without disorder around the same time. And so what's funny is that with Mark, we worked on that simultaneously to you in Rome without knowing that we were doing things so similar. But actually, we discovered later, I think Dave sent me a paper when we published our own paper that we completely missed, in that Ted and Dave published in 1989 in JPhys A, which I think is a truly remarkable paper as well. It's very hard to read, actually. It's so short, but anyway. And everything is there. So this is a density functional Hamiltonian for the glass. There's here a random field term that's added. And if you read the paper, they speak about self-generated static random noise, which is the same as self-induced disorder. And they also say something that we realized later, that adding some randomness and then putting the randomness to 0, which seems weird, is a way to use replicas and get something non-trivial doing that. So, 89. So we were also convinced around 97 that mode coupling theory was accompanied by a diverging length scale. And actually, Goetze and his team were always insisting that mode coupling theory was purely local. It was the formation of local cages with no diverging length scale accompanying the dynamical slowdown, or dynamical arrest, actually, in the theory. But again, KTW had already understood this. In one of their papers, many years before dynamical heterogeneities became topical, they have somewhere in their paper a diverging susceptibility and a diverging length scale around the dynamical temperature. In 95, Silvio and Giorgio came up with another way of understanding this fragmentation of the phase space, introducing their replica potential, which I think shed a very interesting new light on the whole theory. And then with Giulio, and again simultaneously to Peter's work in 2004, we tried to reformulate this thing that I had a hard time swallowing in the early 90s. This nucleation picture, we tried to understand it in terms of a self-consistent cavity melting argument. So I guess that many of you have seen this picture, which I've stolen from a paper by Ludovic and collaborators. So the idea that we had is that even if you froze by fiat all the particles outside some cavity, then the notion of a state cannot make sense when the configurational entropy becomes larger than the pinning energy that's provided by these random boundary conditions. So in that case, one finds exactly the same scaling law as was anticipated in the 1989 paper, but I think on a slightly firmer ground. And also this idea of a cavity is a kind of Gedanken experiment that can be realized numerically and maybe experimentally as well. Something else that we discussed in our paper with Giulio is that maybe the energy barriers scale with a different exponent psi as compared to the surface energy, calling psi after the droplet theory papers of Daniel and David Hughes. So that was around 2004, and then with people here, we got the first numerical experiment showing that something like this seems to happen in model classes. Okay, so well, in the end, is this random field or random first-order transition scenario, which, as I said, I think is beautiful from a mathematical point of view and seems to have a lot of what's needed to build a first-principle theory of glasses. Is it relevant at all for experiments? And this view, is still shared by some people on the planet, and in particular, Jim Langer said, I don't think that these mean field models can be used to predict the divergence of the viscosity of glasses. It's hard to believe that long-range interacting spin models with weird interactions, p-spins, can teach us anything about molecules that stop jittering around. And it's true that it's hard to think that there's such an analogy between models that are so different. But so the answer to this, I think, is that what's remarkable about all this picture that I've shown you, in particular this fragmentation of the phase space, is that even if it was derived, as I said, in a very precise way on mean field p-spin glasses, the underlying mathematical structure appears to be very generic. It's a little bit like the Ising model, where we know that the Ising phenomenology is much broader than the Ising model itself. So for example, more realistic, exactly soluble model of glasses are also RFOT, like lattice glasses or hard spheres in large dimension, with the papers here. Interestingly, any reasonable approximation of first principle Hamiltonians leads to RFOT structure, like replicated state liquid theory, papers by Marc and Giorgio, and also Hajime and Marc. But also frustrated Coulomb models. If you try to use approximations to solve it, then you find again this RFOT structure. And even in the simplest case of the dynamics of a single particle in a Gaussian random potential in large dimension, then the structure of the problem is either RFOT or one-step RSB or full RSB. And there's a nice paper by Laetitia and Pierre in '97. So again, although the theory seemed to be very narrow in the way it was derived, it seems that it has a very broad degree of generality. So consensus and dissent, as I said, some people don't believe in all this. They assign all the Arrhenius relaxation and the Adam-Gibbs entropy correlations to something else, and in particular to the behavior of the high-frequency shear modulus with temperature, which is supposed to capture everything that happens in glasses, even without really relying on any growing length scale at all. Or the other path is to assign everything to kinetic constraints, for which thermodynamics plays no role at all in the slowing down. And then, Adam-Gibbs correlations are just argued to be merely accidental, but have nothing to do with the underlying phenomenon. So, the debate is still raging, I guess, with some rather recent papers by Mathieu Vierre and Mike Cates on this. Still, it seems that all the theories, even the ones that are far from RFOT in spirit, they appear to rely on the existence of a special temperature or a special density where the system becomes locally rigid, where this idea of free flow, unencumbered, to something that is costly to move, seems in all these theories to happen at some well-defined temperature. And so this idea of something like a mode coupling temperature or a Goldstein temperature must arise from somewhere. And at least in RFOT, there's a well-defined reason for this to happen. I think one of the reasons all this is still very controversial is, of course, that all the length scales, all the divergence are cut off, and length scales are bound to be small in this problem. And so all the sharp predictions of MCT in particular, or FOT, are blurred in finite dimensions far from TK, which in any case is going to be hard to reach, except by doing some tricks that Ludovic will tell you about later. So this is a kind of artist view of the situation that we proposed in our review paper with Giulio in 2012 in a book that Peter edited. And so it's a kind of artist view of what I think is the problem and the complexity of the situation. So here in the x-axis is time. Actually, it's 1 minus the correlation function. So when the correlation function is 1, effective time is 0, and when the correlation function is 0, time is infinity, but this effective time is 1. And the y-axis is temperature. And so the idea is that there are different regimes here. So there's this dynamical transition, this MCT transition, which is only going to govern, in any case, the short time regime. In the long time regime, we know that barriers don't grow to infinity, so there's going to be barrier crossing. So at long times, the dynamics has to be governed by barriers and by activation anyway. And then, it's a small sliver here where MCT phenomenology is going to hold. Above this temperature, one expects free flow, but at long enough times, below some onset temperature, there might be some rare regions that are already activated, and these rare regions are going to be dominant at long times. And of course, this regime here is the regime where the mosaic picture should somehow hold. So because of this, the fact that this region is so small is going to be always difficult to be sure that the sharp predictions are relevant. Okay, so to conclude, the strong points of RFOT is, as I said, a unifying mathematically consistent framework for all the classic phenomenology of glasses. In particular, the generic existence of many stable configurations as soon as the system is complex enough. We believe that a glass needs some level of complexity to exist. If the system is too simple, it's never going to get trapped in a rough energy landscape. It suggests the existence of a true thermodynamic amorphous order state, which is either transient on the scale of the relaxation time of the system. Beyond this relaxation time, it's of course a liquid, so all this amorphous order kind of unravels and goes away. But it can be stabilized by cavities, as I said, or by frozen obstacles, or by the trick of coupling the system to another replica with some coupling constant, and I leave this to Ludovic later to tell you about the recent progress. Something, of course, that we've been involved in with Giulio and the experimental group in Saclay and also in Augsburg is the idea that I told you at the beginning of the presentation, the fact that in spin glasses, amorphous order is accompanied by the divergence of a nonlinear susceptibility. This should also be the case in the RFOT picture, but only at non-zero frequencies. So in spin glasses, this divergence of the nonlinear susceptibility should happen at zero frequency, whereas here it's only going to be valid at non-zero frequency. And this prediction seems to be borne out by experiments where you see a growth of the nonlinear, the cubic, and the fifth order susceptibility close to the, as the temperature is reduced, suggesting the existence of something non-trivial thermodynamically in the system. So what are the open questions and some prospective ideas? I think what's really wanted is a much better knowledge of the nature of activated events in the mosaic state, and in particular, what are these barriers, delta psi to the psi. Psi numerically seems to be around 1, which is small and not really compatible with simple bounds one could come up with. And there's also this mystery that the shoving model is exploiting a lot, and all these people thinking that RFOT is not really relevant, is that the product of the log of the relaxation time times the temperature seems to be, well, nearly proportional to the high frequency shear modulus. And that's something that's not completely natural in the RFOT, but maybe Peter will have comments on that. As I said, the nature of the MCT activated crossover is really needed to be more quantitative about this phase diagram, or this picture here, and some ideas have been proposed in the literature more recently, I guess, by Rizzo et al. And some other groups. Let me just point out a few directions maybe worth exploring that we suggested in our review paper. For example, RFOT predicts that as you quench the system, there should be a slow decay of the excess energy or the excess volume as a function of time that is as 1 over log of some power, which includes theta and psi. So maybe that's another route to obtain relation between these exponents both experimentally and numerically. We also discussed what happens within RFOT when you shear the system. And what is interesting is that RFOT suggests a sharp crossover between a high viscosity Newtonian liquid at low shear, at low external stress, to shear thinning when the stress exceeds some threshold, which is given by comparing the elastic energy in a glassite of size psi to this pinning energy. So that would be interesting also to see whether this is true experimentally or numerically. And recently, my beloved wife and her PhD student started looking at experiments where you go from a liquid to a glass and you try to break it. So of course, when you try to break a liquid, it flows, and when you try to break a glass, it breaks. And so there's an interesting phenomenology in between the two. And I think RFOT has interesting things to say about this, in particular the existence of hysteresis between a high velocity and a low velocity branch. So I think this is pretty new and interesting to continue. On that note, thank you very much for your attention.
Many thanks for this masterful summary of 30 years of work. So, do we have any questions?
Yes, Daniel has one.
I guess a general question about another possibility. So, I mean, years ago, decades ago, Charles Braden had developed various Tiling models in the continuum, which don't break they have no Bragg peaks, they don't break rotational symmetry in direct observables, but nevertheless they have them full periodic and they have a so, I mean, so they think one possibility is that there is something like that, which at least in principle, some models would have a phase transition at positive temperature. And is that ever, I know at one point people would talk whether there's some underlying ideal glass state or not, but is that something which has been pursued, or what is?
Well, in this case, you have an ideal glass transition as well, right? TK is an ideal glass transition.
No, but in a real,
okay.
sense where equilibrium and so on.
Well, here too. I mean, if you were able to reach equilibrium at TK, you would be in an ideal glass of that kind. So there is an ideal glass. So what's interesting is that at least here.
Crossovers there and so on.
Then I think I can answer your question. That idea was actually present in, for example, Simsluzel Wallace at the time, and it hasn't been pursued in a very deep way. Doug Levine has done something interesting about it recently, but it hasn't been put yet into a full framework that you calculate rates or anything. But there's been very little work, but Doug Levine has done a little work.
But maybe, I mean, as I was suggesting, maybe if you find such a model and try to actually solve it, it might actually, in the end, show again the same. Yeah. Okay.
So classes break translational symmetry, and then you will have Boston bonds, which should produce long-range effects. When you, for example, have a density fluctuation, it will create some elastic strain which propagates to very long distance. Why there is nothing about elasticity? Is what you say, or
no? Yes. Okay. I agree that. Yes, I think this is what you say is a lot related to having a better understanding of the nucleation events. For example, I think that, as you said, these spins don't have elasticity, and clearly this is probably something that needs to be. But there's a lot of work on that more recently as well. People thinking about elastic events and how localized elastic events propagate to long distances. Okay, well, thank you very much.
I would like to make a comment. I just thought that was a brilliant summary that even KT and W can't object to.
Well, let's thank John Phillips.